Chapter 32, Nuclear Physics and Nuclear Radiation. Here is the overview of Chapter 32. We will first talk about the constituents and structure of the nuclei, then move on to radioactivity, talk about half-lives and radioactive dating, which is related to radioactivity. Then we will talk about the nuclear binding energy, nuclear fission, nuclear fusion, some practical applications of nuclear physics, and we will finally talk about elementary particles. Nuclei contain both positively charged protons and neutrally charged neutrons. We characterize these numbers in the following way. The letter A is short for the mass number, which is the total number of protons and neutrons, and together we refer to protons and neutrons as nucleons. The number Z is the number of protons in the nucleus, and if the nucleus is neutrally charged, this number will equal the number of electrons that surround the nucleus. Finally, we have the letter N that represents the number of neutrons. Therefore, it is pretty straightforward to show that A has to equal Z plus N. Now, there is a particular notation that we use for an element with respect to the atomic number Z and the mass number A. We write it down as follows. The X represents the element that we are notating. The Z on the bottom, which is the number of protons, will represent the atomic number, and the A at the top will represent the mass number, which is the number of protons and neutrons. We have a couple of examples here. We have carbon 14, where the 6 represents the number of protons, which is always 6 for the carbon nucleus. The 14 is the number of protons and neutrons. In this case, we need to have 8 neutrons and 6 protons to get a mass number of 14. On the right, we have aluminium, where the number of protons is 13, the Z number, and the mass number is 27, which means we need 14 neutrons. The proton itself has a mass quite similar to the neutron. See the table for a comparison. The only difference is the charge of a neutron is 0 and the charge of a proton is 1.6 by 10 to the minus 19. The mass unit U we will talk about in the next slide. The mass unit mega electron volts per c squared comes from relativity, and we will also talk about this on the next slides. The atomic mass unit U is defined so that 12 times U, so 12 of these mass units, is exactly equal to the mass of a carbon 12 nucleus. In other words, if you take the carbon 12 nucleus and divide it by 12, that will give you one of these mass units. The translation to kilograms is 1U is equal to 1.660540 by 10 to the minus 27 kilograms. We can also write the mass in terms of mega electron volts per c squared. This comes from relativity. Mega electron volts is a measure of energy, and c squared is the speed of light squared, and 1 atomic mass unit is equivalent to 931.5 mega electron volts per c squared. Again, we use electron volts, and the conversion to joules is 1.6 by 10 to the minus 19 joules. Now, we can relate the approximate size of the nucleus to the atomic number. If we think of the nucleus as a sphere, the radius of that sphere, r, will equal 1.2 by 10 to the minus 15 meters times a to the power 1 over 3, where a is the mass number, which is the number of protons plus neutrons. Now, the typical radius of the nucleus is on the order of 10 to the minus 15 meters, and if we compare that to an atom, which has a radius of 10 to the 10 meters, and this radius of the atom is dictated by the size of the orbit of the electron, since all of the mass of the atom, or 99% of the mass of the atom, exists within the nucleus, this shows that the density of the nucleus must be extremely high. For convenience, we have a measure of length that is suitable for nuclear scales, and that measure is the Fermi meter, and 1 Fermi meter is equal to 10 to the minus 15 meters. We also refer to this as simply 1 Fermi. Now, an interesting question is that if the nucleus only contains positive charges and neutral charges, the positive charges coming from the protons, why does it not fly apart? And the answer is there is another force which can overcome the electric force, and this force we refer to as the strong nuclear force. This is an attractive force, and it keeps the nucleus together. The properties of the strong force is that it is short range, it only acts at a distance of a few Fermi. Beyond those distances, the force strength is very low. It's always attractive, and that's how the nucleus is kept together, and the strong force has an equal strength irrespective if you have a proton-proton interaction, proton-neutron, or a neutron-neutron. The strength of the force is always the same, irrespective of which nucleons it acts upon. Here we have a graph that shows how the number of neutrons compares to the number of protons for largely stable nuclei. The solid line is the expectation that the number of neutrons should equal the number of protons. This is definitely true for small nuclei, such as a helium nucleus that has 2 protons and 2 neutrons, but as the nucleus gets larger, as we have something like 70 protons, we need many more neutrons in order for the nucleus to be stable. Typically, a nucleus of 70 protons will need about 100 neutrons. If one starts to increase the number of neutrons relative to the protons or decrease, the nucleus becomes unstable. As we'll discuss next, it can decay, and it will either decay by emitting a beta particle or an alpha particle. As mentioned, these unstable nuclei can either decay into a stable nucleus of a different N and Z, or they can return to the ground state from an excited state. And in this case, the number of protons or neutrons doesn't change. You just have a very energetic nucleus that becomes a less energetic nucleus. The first type of decay is an alpha decay, where an alpha particle is emitted, and an alpha particle consists of 2 protons and 2 neutrons, and it is the nucleus of a helium atom. The second type of decay involves the emission of electrons or positrons. For historical reasons, we refer to these as beta decays or beta rays. A positron has exactly the same mass as an electron, but it is positively charged, and that positive charge is exactly the same positive charge as a proton. It is in fact the antiparticle of the electron. The third type of decay is a gamma ray decay, and these are very high energy photons that are emitted from the nucleus. Now, in terms of the penetrating abilities, and by this we mean how far these particles can travel in some sort of medium, and alpha ray can barely penetrate a sheet of paper. Beta rays can go further, and it takes a few millimeters of aluminium in order to stop these rays, and finally gamma rays can penetrate several centimeters of lead, which means out of all of the types of radioactive decays, these ones can go through the most material. When a nucleus decays by emitting an alpha particle, it loses 2 neutrons and 2 protons in the process. We can write our element on the left-hand side, where A is the mass number and Z is the atomic number and X is the type of atom. Upon decay, we will lose 4 nucleons, which means the mass number will be reduced by the number 4, and we will lose 2 neutrons, which means the atomic number will be reduced by the number 2. To conserve these numbers, we emit a helium atom in the process, which is the alpha particle, and this will of course have a mass number of 4 and an atomic number of 2. On the right we have an example where uranium decays to thorium and an alpha particle. In the process of this decay, we actually have an energy release, just as we do for chemical reactions. Now, a beta decay does something different. A beta decay involves the emission of an electron or a positron, and in doing so, one can either convert a neutron into a proton and emit an electron, or we can convert a proton into a neutron and emit a positron. In either case, one has to make sure that charge is conserved, so when the neutron turns into the positively charged proton, we have to have a negatively charged electron in order to balance the charge. When this happens in a nucleus, what we find for a electron emission is, because a neutron turns into a proton, we gain an extra proton, and that increases the atomic number. However, the mass number stays the same because the number of protons and neutrons is still the same. When the nucleus emits a positron, we have a proton that turns into a neutron. Because of that, the atomic number is reduced by 1, and we emit a positron in the process, since the proton is now a neutral neutron, so there has to be a positive particle emitted, which is the positron. As mentioned before, a gamma ray is emitted when an excited nucleus returns to a ground state from an excited state. It can get to an excited state via a previous decay. One example is a carbon-14 can beta decay to a nitrogen-14, and the nucleus that it beta decays into, the nitrogen, is an excited state. It has more energy than it needs. Once this is made, then this excited state, which is denoted by the asterisk, can lose energy, and one will produce a photon in the process. So n star goes to n plus the gamma ray photon. Now, it often happens that nuclei that decay into other nuclei, the other nuclei are also unstable and they can decay into something else. This will happen, and it will continue to happen until a stable nucleus is reached, and that typically is a lead nucleus or something with a lower mass than the lead nucleus. Here we have an example on the right where we have a uranium. This will decay via an alpha to thorium. Thorium then can decay itself via a beta decay into something else, and this process will continue until we reach a lead nucleus on the bottom. Some decays happen more rapidly than others, and we can actually measure the rate of decay when we have many nuclei that are decaying, and this rate is the number of decays per second, and it is referred to as the activity, or indeed the radioactivity. There are two units for this. One is the Curie, which corresponds to 3.7 by 10 to the 10 decays per second, or the Becquerel, that corresponds to 1 decay per second. The Curie and millicurie and microcurie is the unit that is most commonly used. Nuclear decay is a random process, and by that we mean that if a nucleus can decay, we don't know at exactly which time it will decay. However, if we have a large number of nuclei, we can predict the decay rate. That number, i.e. the number that haven't decayed, which is capital N, after time t, will equal n0 times e to the minus lambda t, where n0 is the initial number of radioactive particles that can indeed decay. Different nuclei will have different decay constants, which is lambda in the previous equation. Lambda controls essentially how quickly a nucleus will decay. The bigger this is, the smaller time it takes for a certain number of nuclei to decay. We have a graph on the bottom where we have the number of nuclei that haven't decayed over the initial number versus time, and we can see the number of nuclei that haven't decayed. That number drops much more quickly for the larger lambda versus time compared to the smaller lambda. At an infinite time, all the nuclei will have decayed, and the red curve goes to 0 as a result. The nuclear decay can also be characterized by the half-life, and this is simply defined as the time it takes for half the sample to decay away. It's related to lambda as follows. The half-life will equal the natural log of 2 divided over lambda. The decay rate or activity, which are the number of decays per second, will equal, by definition, delta n over delta t, and this will equal lambda times n, which is the number of radioactive nuclei that haven't yet decayed. The activity as a function of time, r, will equal some initial activity, r0, times by e to the power minus lambda t. The change in activity over time is something that is very useful in determining how long an organism has ceased living. Any organic material or organic matter will have the same ratio of carbon-14 to carbon-12. Since carbon-14 is radioactive, when an organism dies, what will happen is the carbon-14 will decay, and since the organism is dead, there is no other source of carbon-14 to replenish this, which keeps this ratio of carbon-14 to 12 constant as the organism is alive. So essentially, by measuring the amount of carbon-14 activity, we can determine how long the organism has been dead for. This is referred to as carbon dating, and it is the main way that we have determined the age of fossils, such as dinosaurs, which we now know died millions and millions of years ago. Now we will discuss the nuclear binding energy. So it turns out that the mass of any stable nucleus is less than the sum of the individual masses of the protons and neutrons it contains. So the mass of the nucleus is essentially smaller than what we might expect. That difference in mass times c squared is referred to the binding energy, and it's essentially the energy that we need to give the nucleus in order to separate it. We have to increase its mass, and the only way we can do that is to give it energy from Einstein's equations of relativity. We can also express the binding energy in terms of the binding energy per nucleon, and this is a measure of the mass reduction of the individual nucleons in the nucleus. Here we have a graph of the binding energy per nucleon versus the mass number. It turns out that iron nucleons have the largest binding energy, which means that it is most difficult to remove a proton or a neutron from an iron nucleus, which actually means an iron nucleus is the most stable nucleus we've found. This binding energy will drop either if the mass number goes down or if the mass number goes up, and it does so in a relatively smooth fashion. Now, any nuclear reaction will involve a loss of mass, which involves an energy release. The loss of mass in a nucleus will translate into a greater binding energy, since this comes from a mass difference. Nuclear fission occurs when a heavy nucleus splits into two lighter ones, especially if it captures a neutron. Lighter nuclei do not need so many neutrons for this process to happen, and typically when it does happen, one will emit many more neutrons in the process. Now, the emission of multiple neutrons leads to a chain reaction, which means more neutrons can hit other nuclei, fission happens, and we get even more neutrons. And in any sort of nuclear reactor that is producing energy from these reactions, one either needs to have this controlled, or in the case of a nuclear weapon, perhaps one would like this uncontrolled. Nuclear fusion is the opposite to nuclear fission, but it actually has the same effect. And what happens with nuclear fusion is two lighter nuclei combine to form a heavier nucleus, but the mass of the heavier nucleus is less than the light nuclei that form the nucleus in the first place. This leads to a smaller mass per nucleon, and that smaller mass is released in the form of energy. Now, this can only happen at extremely high temperatures because one has to get the nuclei to overcome the electric repulsion, which becomes very strong as the nuclei come close together. An example of nuclear fusion is the center of the sun. That's essentially the main source of energy in the sun is nuclear fusion releasing energy, mainly in the form of photons, which reaches the Earth. And many other stars also undergo this process, and that's what makes all the stars bright in the sky. Here we describe the actual process of nuclear fusion in the sun. It starts off by two hydrogens combining to make deuteron, which is a hydrogen with one proton and one neutron. Then a deuterium can combine with a normal hydrogen, and this makes helium-3, where the helium has two protons and one neutrons. After that, a hydrogen can combine with a helium-3 to make a helium-4, or two helium-3s can combine to make one helium-4 and two hydrogens. This, or all of these interactions, they emit a considerable amount of energy, and these are the main interactions that ensure that the sun shines bright. Nuclear radiation can be very beneficial if used properly, but it can also cause tissue damage if used improperly. There are a number of ways to assess this damage. The first is to measure the amount of ionization. Radioactive particles are very energetic, and they can essentially liberate electrons from atoms and cause ionization in the process. The Roentgen is a radioactive dose that creates 1.58 by 10 to the minus 4 coulombs of charged matter when the radiation passes through 1 kilogram of matter. The definition is therefore 2.58 by 10 to the minus 4 coulombs per kilogram. Another measure is the amount of energy absorbed by something that has been subjected to radiation. We refer to this as being irradiated, and the unit is rad, and 1 rad corresponds to 0.1 joules of radiation energy absorbed per kilogram of the irradiated material. One thing to note, though, is, however, the same amount of energy of different types of radiation can lead to different biological effects. For instance, if the same amount of energy came from gamma rays compared to alpha rays, the type of radiation damage could indeed be different, even though the energy is the same. In order to quantify these differences, we define another measure called the relative biological effectiveness, which is written as RBE. This is equal to the dose of 200 keV X-rays necessary to produce a particular biological effect divided by the dose of a particular radiation that's necessary to produce the same effect. Here is a comparison of RBE for different types of radiation. So we've discussed alpha rays and beta rays and gamma rays, but there are other types of radiation such as fast neutrons, slow neutrons, protons, and heavy ions. The bigger this number, essentially the more effective the radiation is, because one needs a smaller dose to produce the same biological effect as a dose of 200 keV X-rays. Now, RBE can be combined with the dose to give the biological equivalent dose, which is measured in a unit called rem, which is rotagen equivalent in man, and 1 dose in rem is equal to 1 dose in rad times the relative biological effectiveness. Here are some sources of radiation that we typically receive throughout the year. Some are natural sources, some are manufactured. The natural sources are cosmic rays, which is radiation that comes from space, and the natural radioactivity in the Earth and the atmosphere. We also can receive radiation from nuclear medicine, medical and dental examinations, and inhaled radon. The amount of radiation is measured via the dose, which is essentially the number of rem per year. Now, there are a number of medical applications for nuclear physics. The first are radioactive tracers, where one places a fluid with radioactive elements and the patient has to ingest this, and the fluid will travel around the body and emit radiation as it does so. One can detect where the radiation is emitted to see if the passage of the fluid is what we would expect for a healthy person. There are also PET scans, positron emission tomography, where a positron electron pair is emitted within the body, and one can look at the emission patterns and diagnose things such as tumours and other sorts of things that are abnormal. The final is magnetic resonance imaging. This doesn't use radiation, but it uses known behavior of how protons behave in a magnetic field. A proton is a nucleus of a sort, and magnetic fields are switched on and off to see how the proton responds to this, and this can be detected all over the body, since the body contains water. By looking to see where the protons are, so to speak, one can look at the distribution of water, and if the flesh is somehow different than we would expect, this should show up in an MRI scan. The final topic of this chapter is elementary particles and forces associated with these particles. There are 4 fundamental forces that we know of. The first is the strong force, and this holds the nucleus together. It has a range of 1 Fermi, and by this we mean the force does not apply itself over distances greater than 1 Fermi, and we define it to have a relative strength of 1. The electromagnetic force, which is 100 times less strong than the strong force, this has a range of 1 over r squared, which is infinite, and this 1 over r squared simply comes from Coulomb's law. The third, which we haven't discussed, is the weak force, and this is a force that's responsible for the beta decay that we discussed previously in the chapter. This is even weaker than the electromagnetic force with a relative strength of 10 to the minus 6, and it has a range smaller than the strong force at 10 to the minus 3 Fermi. The final force is the gravitational force. This is the force that keeps the planets in motion, and this has a relative strength of 10 to the minus 43, which is much weaker than all of the other forces, as we see. This range is also infinite. It goes as 1 over r squared, and this simply comes from the law of gravitation. There are two types of fundamental particles, leptons and hadrons. Leptons usually interact via the electromagnetic force if they are charged, or the weak force. Here is a table of the known leptons. We have the electron, muon, and tau, and the electron neutrino, muon neutrino, and the tau neutrino. Here we show the symbols, the mass, and the lifetime of the particle. By lifetime, it turns out that the muons and taus, if they're produced, will only last a particular time until they decay into something else. Hadrons are particles that interact via the strong force. They come in two varieties, baryons and mesons. Protons and neutrons are examples of baryons. Here we have a table, again, with the symbol, rest energy and lifetime. The rest energy, which is equivalent to the mass for a proton and neutron, are similar, and we can actually make particles with a higher mass. One example is the sigma and the omega, but it turns out that these are not very stable, i.e. they decay into other particles pretty quickly. Here we have a table of mesons, and these are usually created by particle accelerators or existing cosmic rays. The three main mesons are the pion, kaon, and eta, and one can see again the mass and lifetime of these. All of these have a finite lifetime, i.e. they will decay after a certain amount of time. Now, leptons themselves have no internal structure. We can consider them point particles, but this is not true of hadrons, however. Here we have the two types of hadrons, the mesons and the baryons, both of which are made up of these things called quarks, which themselves have no internal structure like leptons. A meson will have a quark and an antiquark, and a baryon will have three quarks. So the pi plus meson has an anti-down quark, which has a charge of minus a third e, and an up quark, which has the charge of 2/3 e. That gives the pi plus meson a charge of plus 1. The neutron has an up quark, which has a charge of 2/3, but it has two down quarks, which have a charge of minus 1/3. When one adds these together, one gets a charge of 0. The proton has two up quarks and one down quarks, and when one adds the individual charges here, one gets a charge of plus 1. Here we have a table of all the known quarks and antiquarks As mentioned before, there is something called an up and a down quark. It turns out there are other types of quark. One is a charm quark, the other one is a strange quark, and we have a top and a bottom quark. All of them have different charges and different masses. Now, quarks cannot exist on their own. They are always found in bound states, either in a baryon or a meson. If you try to disattach a quark from one of these states, more quarks are made in the process to make more hadrons or mesons.